Hello dear friends, I welcome you all for the lecture number 11 on a Hammett linear free energy relationship. In this lecture we will discuss about the top equation which is applicable only for the aliphatic esters, which is applicable for the aliphatic esters. Now we have already derived the Hammett equation. We have already derived and discussed the Hammett equation in previous lectures. And this equation is only applicable for the sorry is only applicable for the meta and para substituted esters. And this equation, Hammett equation, is not applicable for the aliphatic and orthoester. Not applicable for the aliphatic and orthoester because they cause the steric crowding during the intermediate formation. During the intermediate formation, they cause the steric effect, and therefore Hammett equation is not applicable for the aliphatic and orthoester, as Hammett consider only the polar effect. As the Hammett equations consider only the polar effect, the aliphatic esters and orthoester for aliphatic and orthoesters, Hammett equation is not applicable. Now, Now the Hammett give the solution for this. Hammett consider Hammett basically the Hammett consider the two reactions. In first reaction, the rate of reaction is depend on the polar effect as well as on steric effect. And Taft consider the second reaction where the polar effect is almost zero and only the steric effect is responsible for the rate difference. Only the steric effect is responsible for the rate difference. And by carrying out these two reactions, uh, and subtracting the reaction number 2 from 1, he equally cancel out the steric effect and the effect that play the important role in the rate difference or that cause the difference in rate is the polar effect. And as we know that whenever there is a no steric effect there, we have a straight line. We have a straight line. So in this way, by giving such a equation, Taft showed the straight line relationship in case of aliphatic esters also. So these two reactions are shown over here. This is your first reaction, which is a base catalyzed ester hydrolysis, having the raw value is 2.51. The raw value 2.51 clearly indicate that this reaction is susceptible towards the polar effect exerted by substituent. Polar effect or electronic effect exerted by this X substituent. Now the second reaction is acid catalyzed hydrolysis, which is having the raw value is equal to point zero 0.03, which clearly indicate that very little or almost zero polar effect is causing the rate differences. It clearly indicate that polar effect or the effect of the substituent X is uh, very less in stabilizing the intermediate, and therefore the effect of X is a negligible, which can be, and therefore we have a very small value of reaction constant. And if we consider the intermediate of the rate determining step, this is the rate determining step for the base catalyzed hydrolysis. If we consider this intermediate formed during the rate determining step, and if we consider the intermediate formed during the rate determining step of acid catalyzed hydrolysis, then you can see that these two intermediates are only differ by two hydrogen atoms. One is shown over here, and another is this one. Here we have a only one hydrogen. One, sorry. So these two intermediates are only differ by the two hydrogens, and therefore we can say that the steric effect is get equally cancel out. As we know that the protons have a very little steric effect, and therefore very little steric effect, and therefore they do not cause the steric crowding. Due to the very small size, protons do not cause the any steric effect, and therefore the here we can have a zero steric effect, as steric effect get cancel out. And from these two reactions, Taft gave the Taft equation, which is applicable for the aliphatic ester. So here this is a comparable rate constant for the aliphatic ester with the standard R group minus the acid catalyzed ester hydrolysis. Rate ratio of the acid catalyzed ester hydrolysis is equal to rho star into sigma star R. Now here the value of sigma star is equal to 2.48, as it come from 2.51 minus 0.03. So by calculating or measuring the rate constants for different reaction, for measuring the rate constant for the different reaction, and by putting the value of rho star, which is equal to 2.48, we can calculate the sigma star. We can calculate the sigma star R for the various reaction. Various substituent. We can calculate the sigma star R for the various reaction. Sorry. Now here top consider K0 is equal to methyl group rather than hydrogen. As hydrogen is methyl is the first alkyl group which cause the steric crowding, or which shows the steric crowding. Sorry. Methyl group is a first alkyl substituent, is a first member which shows the steric crowding, and therefore K0 is for methyl CO2 ether, and not for the K0 is equal to not a. In short, methyl is a reference substituent. In this reaction, methyl is a reference substituent. Sorry, methyl is acts as a reference substituent, and K0 is equal to rate of a ester hydrolysis of this ester, that is MeCO2 ethyl. So this is about the Taft equation. Now this Taft equation is for the ester hydrolysis of aliphatic ester. Now if we want to compare the series of reactions, not ester hydrolysis, series of various reactions, where R is a aliphatic group, then we can use this general form of Hammett type Taft equation, where by calculating the by calculating the rate, or by rate measurement, and by having the value of sigma star R from the previous Taft equation, we can easily calculate the rho star for that particular reaction. I am repeating here, any reaction other than ester hydrolysis, or to compare the other reactions other than the ester hydrolysis, uh, this is we have a general form of Hammett type equation for that, where we can easily measure, or by kinetic measurement of this, or rate measurement of this various aliphatic groups, various R group to the standard reaction, and by having the sigma star R from the previous equation, we can determine the sigma star sorry we can determine the rho star for the various type of reaction. Thank you.